What is this? The effect of a stream of particles shooting through space like little machine gun bullets? Or is this a procession of fast-moving waves? Or are there both here? And are you really watching light at all, or merely where it comes from? Watch, as from these apparent contradictions, science finds a universal property of all forms of existence.
It should go without saying that nature can never contradict herself. To say she contradicts herself would be to say something that has no meaning. There are times, however, when nature seems to contradict herself, when we find in nature facts that seem utterly inconsistent. These are the paradoxes of nature. They are fascinating to the scientist, riddles that challenge his understanding.
It all began with the problem of the nature of light. By light we see. Through its darting rays, we maintain a continual living contact with the world around us. Light from the sun and the accompanying invisible light-like rays of radiant heat bathe the earth and make it warm and habitable. Just what is light? Since the 17th century, there have been two competing theories regarding the nature of light. According to the corpuscular theory, a beam of light is a stream of tiny particles, or corpuscles, ejected by the light source, whether it be the sun, or a star, or a man-made lamp. According to the wave theory, on the other hand, a beam of light is a stream, or train of high-speed waves that are radiated by the light source as sound waves are radiated by a vibrating tuning fork. To illustrate the problem, let me form a beam of light by placing this sheet containing a round hole in front of a small and brilliant source of light. Now notice that you cannot see the beam unless you scatter some chalk dust across its path, and so scatter the waves into your eyes. Or you can locate its path by intercepting it with a sheet of cardboard. You can't tell whether light is like machine gun bullets or like a train of waterways by merely looking at it. The reason is that vision consists not in seeing light, but in seeing where it comes from. We're all warmed by the rays of the sun, so light must carry heat energy with it from place to place. It travels with enormous speed in lines that are generally straight. This could be done, of course, by flying corpuscles like machine gun bullets, as in this diagram. But it could also be done by a train or stream of waves. No other plausible interpretation has occurred to us. But the question is, which is it, waves or corpuscles? This question was argued by Isaac Newton and Christian Huygens back in the 17th century. Newton took the corpuscular point of view, but Huygens preferred the wave theory. In the 19th century, new facts about the behavior of light were discovered that seemed to decide the question once for all in favor of Huygens and the wave conception. But paradoxically, still other facts discovered in our own century have forced us to revive the corpuscular point of view. In Newton's opinion, the fact that light travels in straight lines and casts sharp shadows could only mean that it is corpuscular. Let's demonstrate this, casting of sharp shadows. Water waves and sound waves bend around corners. they do not lend themselves to the casting of sharp shadows. So Newton argued that light cannot be a wave motion. This argument, however, is convincing no longer. Today, we know much more about wave motions than Newton did. We've discovered, for example, that when a train of parallel waves strikes an opening in a barrier, the extent to which it bends around the edges of the barrier depends both on the wavelength and on the size of the opening. For example, here is a picture of a train of ripples passing through an opening in a barrier. The dotted lines show the edges of the beam that would be formed if the waves cut off sharply. But as you can see, the waves spread beyond these dotted lines. Just the same, the train of emergent waves does form a crude beam. Now here, I've marked in a single wavelength, running from the crest of one wave to the crest of another. By shortening this wavelength, you can sharpen the beam, causing it to remain more closely within the dotted lines. These, of course, were ripples on water. Light waves are much shorter. But actually, even a beam of light spreads a little at the edges and casts shadows that are not perfectly sharp. In fact, the spreading of light waves fits the wave theory perfectly once we understand how very short light waves are. So, Newton's objection, based on these sharp shadows, is turned into an argument in favor of the wave conception instead of the corpuscular conception. There are many such arguments, but the strongest argument for the wave theory of light is the fact that overlapping beams of light can produce the phenomenon of interference. Suppose, for example, that we have a thin sheet of metal in which two small parallel slits have been cut, such as this. Imagine two such slits placed in front of a beam of light from a distant small source. If the slits are narrow enough, and they must be very narrow and close enough together, the two slender beams emerging on the right will spread enough to overlap each other. By intercepting the light with a cardboard screen or a photographic plate, you can study the distribution of light intensity in the region where the two beams overlap. This is what you see on the screen or developed plate, a pattern of vertical stripes. Either of the two overlapping beams by itself would produce a simple patch of light like this. But when the beams overlap, the patch is crossed by dark stripes. The two beams combine in some places to produce darkness. This we call interference. It is a mutual cancellation of the two overlapping beams that takes place in certain narrow zones of the overlap region. Such a cancellation is hardly conceivable if we think of these two beams as two streams of machine gun bullets. The streams of fire from two machine guns always reinforce one another. They can never cancel out. On the other hand, this interference is exactly what we would expect from the wave theory. For example, the same thing happens with the ripples on the surface of water. Here there is a shallow pool of water lit from a lamp below in such a way that we can see by projection what happens when the water is agitated. The agitation is accomplished by a metal finger, which can be made to vibrate in the water. Let me start it. You can see a regular train of expanding circular waves with a definite wavelength, a definite distance between the crests of successive waves. One vibrating finger, one set of ripples. But now suppose I use two. When both fingers oscillate in unison, they produce two similar ripple systems that cross one another as they expand. You can see on this photograph zones of strong wave motion, and between them lines like the aisles in an amphitheater where there is little or no wave motion. Why? In the zones where there is strong wave motion, the crests of one wave train meet the crests of the other. In the same zones, the troughs of one system meet the troughs of the other. Here, then, the two wave trains cooperate. But along the lines that mark the aisles of our amphitheater, the crests from the right meet troughs from the left. So the two motions cancel one another, and here we have interference. Now, in the case of optical interference, two slits, much smaller and closer together than these, take the place of the two fingers dipping into water. But the same alternating zones of cooperation and interference exist in the overlap region. But to make them visible in this case, we must catch the light on the screen or a photographic plate. The existence of such alternating bright and dark bands shows that light does have the properties of a wave motion. The spacing of the bands depends on the distance between two successive crests. In other words, on the wavelength. Using such interference bands, scientists can actually measure the wavelength of light. It turns out to be extremely small, about a 50,000th part of an inch for green light. This is much smaller than the smallest dust particles you can see with your naked eye, but much larger than, for example, the diameter of an atom. Now, ordinary white light is a mixture of many different colors and corresponding wavelengths. You are familiar, I am sure, with the effect produced by a prism when placed in the path of a beam of light. When white light strikes the side, the rays are bent toward the base. The shorter waves are bent more than the longer ones, and this causes a separation of the different colors. Without color television, you won't be able to see the resulting rainbow effect. Lights out. Is the band of color on the screen that passes from red on the right through orange, yellow, blue, green to violet. The colors are arranged according to their wavelengths, the red on the right being the longest. But this is far from the whole story. In addition to the wavelengths to which our eyes are sensitive, there are other wavelengths, invisible colors, so to speak, that lie beyond the violet end of the visible spectrum. These are the rays that produce sunburn at beaches. Other invisible colors with wavelengths longer than those of visible light can be detected beyond the red end of the spectrum, out here. These are classified as infrared light or radiant heat. These infrared rays are primarily responsible for the warm glow from a fireplace. But this is not all. We have gradually discovered how to generate and study radiant energy with all wavelengths from several miles to a fraction of a billionth of an inch. Here's a chart that shows them all. On one end, we have radio waves, which may be as much as a mile long. Then we have microwaves, centimeter waves used in radar. Then the infrared heat waves. Then this narrow visible spectrum with red here and blue over there. Ultraviolet light. Then X-ray region. And finally, gamma rays, with the wavelength getting shorter and shorter as you go across the diagram. Now, all these different classes of radiant energy are generated in different ways. Though they differ from each other in some respects, they are alike in others. For example, all travel through a vacuum with the same speed, 186,000 miles a second. And in each case, from radio waves to X-rays, the enormously different wavelengths are measured by a suitable adaptation of the same method of interference. But now, after all this build-up about the wave theory, here's the paradox. There are still other facts about light and other shortwave forms of radiant energy that seem to contradict the wave conception flatly. These other facts have to do with the way in which short waves interact with matter. For one thing, it is necessary to use increasingly violent methods to generate radiant energy of shorter and shorter wavelengths. A poker heated to a moderate temperature glows dull red. It emits almost no blue light. To generate blue light, the temperature has to be stepped up sharply. And to generate ultraviolet light, we have to use the violence of a heavy electrical spark. Let me show you. To produce X-rays with even shorter wavelengths, we have to form a beam of high-velocity cathode rays in a vacuum tube and use it to bombard a block of heavy metal. The greater the energy of the cathode rays, the shorter the wavelength of the X-rays they generate. Violent effects are evident when short waves are absorbed by matter, and that by this I mean waves all the way from the visible on through into this gamma ray region. Ultraviolet light and X-rays ionize the atmosphere. That is, they tear apart the molecules of oxygen and nitrogen that make up the air, forming positively and negatively charged fragments called ions. The longer waves of visible light and infrared light cannot do this, nor can the longer wavelengths produce sunburn. That comes from the ultraviolet in the sun's rays. An overdose of X-rays with their super short wavelengths quickly produces much more dangerous burns. But although these indications of violence are strikingly dependent on measured wavelengths, they are not easy to understand in terms of the wave theory. There's no apparent reason why waves of high frequency and short wavelength should be harder to generate or more destructive than those of long wavelength. We can delve a little into these remarkable properties of shortwave radiation by means of a technique first used in the study of the so-called alpha and beta rays. These are high-velocity particles of matter given off by radioactive substances. When these rapidly moving particles pass through the air, they ionize it just as X-rays do. If ions are formed in air saturated with moisture, the water tends to condense on the ions in tiny droplets. In a specially designed cloud chamber, as it is called, it is possible to convert an invisible trail of charged ions into a visible track of water droplets. This visible track is not unlike the cloud track left behind by a speeding jet plane on a clear day. Here is a photograph of a sheaf of alpha tracks from polonium. Each track is composed of many tiny drops of water. You can see that most of these tracks end at about the same distance from the radioactive source. The rays are slowed down as their energy is used in the production of ions, and each track ultimately terminates the point where the alpha is brought to rest. Such cloud chamber photographs reveal many sorts of events in the atomic world. For example, here alpha particle sharply deflected by a collision with the nucleus of a chlorine atom. So far, you've seen only tracks produced by alpha particles. On the other hand, beta rays, electrons, are much lighter and hence more easily deflected. Here you can see that their tracks are more irregular than alpha tracks. However, very fast beta particles do have straight and very thin tracks, such as you see here. So much for the effects produced in a cloud chamber by alpha and beta particles. But what happens when we send a beam of short wavelength radiation through a cloud chamber? For example, a beam of light-like but invisible X-rays. Are the ions produced by the X-rays strung along trails directed, like the tracks of alpha particles, along the path of the beam? If this were the case, it would prove that X-rays are like the corpuscular rays of matter. But since X-rays have wave properties like light, we do not expect this. It would seem more likely that the ions produced would be scattered over the entire space swept by the X-ray beam. Indeed, this can happen, as you see here. But to get this effect, we must use X-rays of extremely long wavelengths. If you use a shorter wavelength of X-rays, this is the result. Shorten the wavelength still further, and this happens. Shorten it again, and one gets a picture of this kind. Clearly, shorter X-rays do generate tracks, but these tracks are not lined up in the direction of the beam. They start in the path of the beam, and then shoot off it up and down. Now compare the appearance of this X-ray effect with this, the track of beta particles. You see the similarity. The tracks left by the X-rays suggest that the particles that produce them are of the same nature as beta particles. They are, in fact, the tracks of electrons ejected from air molecules with sufficient speed and energy to form ion trails. We call these photoelectrons. From the point of view of the wave theory of light, these photoelectrons, these electrons ejected from atoms by light, are very remarkable. The energies of the individual photoelectrons are unaffected by variations in the intensity of the X-ray waves. However, if the wavelength of the X-ray beam is shortened, the energy of the photoelectrons is increased merely by shortening the wavelength and increased to any desired amount. This is not the kind of thing we would expect from the wave theory of X-rays. A wave motion could not of itself provide the concentration of energy needed for such a violent effect. In fact, the phenomenon suggests that X-rays are not waves at all, but a barrage of explosive shells or packages of energy that can explode in an atom and deliver their whole energy content to a single electron, thus turning it into a photoelectron. In fact, there seems to be no escape from the conclusion that X-rays have corpuscular properties as well as wave properties. Like Dr. Jekyll and Mr. Hyde, they have a dual personality. And if this is true for X-rays, it must be true for all other forms of radiant energy from one end of the chart to the other. Therefore, we assume the existence of energy corpuscles in radiant energy, and we call them photons. Remember, they are not the same as photoelectrons. They are the explosive shells which produce photoelectrons. By measuring the energies of photoelectrons whose tracks we see, scientists can work backward to infer the energies of the photons that leave no tracks. These energies increase as the wavelength becomes smaller and smaller. Now think back a minute or so to the explanation of the production of X-rays. You can see now why it is that high-velocity cathode rays are needed to generate short wavelength X-rays with their powerful photon energies. To create these high-energy photons, you must have cathode rays of equal or greater energy. You can also understand why X-rays and ultraviolet light are dangerous. When they fall on living cells, their photons produce photoelectrons, just as they do in air. If the cells are in our own muscular tissue, the photoelectrons tear through the tissue and produce destructive ionization wherever they go. Now you see the paradox. Only a wave theory can explain the interference experiments by which we measure wavelengths. Only a corpuscular theory can explain the explosive ejection of photoelectrons. Waves are conceived to be continuous disturbances whose energy is thinly spread out in space, whereas photons or light corpuscles are flying pinpoints of concentrated energy. Common sense tells us that life must be one thing or the other, but the facts will not have it that way. Does nature contradict herself? By no means. What she does is to force us to conceive of light and other forms of radiant energy as something that spreads out in space as if it were a wave motion, but which interacts with matter as if it were a barrage of explosive shells. Perhaps we should think of waves as guiding corpuscles. In any case, we must certainly retain parts of the wave conception and parts of the corpuscular conception for a complete interpretation of all the facts. Now, at first, this uncomfortable hybrid point of view met with strong resistance among scientists. However, this resistance was greatly reduced when it was shown 20 years ago that electrons and atoms have the same paradoxical combination of corpuscular properties and wave properties that light and X-rays have. If this setup is used to send a beam of X-rays through a box of powdered crystal, the rays are scattered in directions which make well-defined angles with the beam. If the scattered rays are caught on a film, they produce a pattern of concentric rings like this. The pattern is due to interference between the wavelets scattered by the atoms in the crystal lattice. we can use this pattern to measure the wavelength of the X-rays. But now, suppose you substitute a suitable pencil of moving electrons for the X-rays in a setup of the same kind. In this case, you produce a similar pattern of concentric rings. This, too, is an interference pattern produced by a beam of electrons, compared with the one produced by X-rays. The similarity means that electrons in motion, like X-rays, behave as if they were guided by waves. We can measure the wavelength by the pattern and show that the relation between energy and wavelength for electrons is in harmony with the relation between energy and wavelength for X-rays and for light. So the dualism of wave and particle is not just a property of light. It is the universal property of all forms of physical existence. The universality of the paradox makes it easier to accept. Moreover, the discovery that matter has wave properties has turned out to be the real key to the understanding of the structure and properties of the atom. Atoms only make sense when we understand that each is both a system of particles and also a complicated system of standing waves like those in a bowed violin string. The discovery and acceptance of this universal dualism of wave and corpuscle is the heart of the great revolution in modern physics and chemistry that we call quantum theory. These ideas, of course, outrage our common sense, but they fit all the known facts. The world of modern physics is built upon them.
Most of the paradoxes of modern physics derive from this, that we can reach, by indirect measurement, physical quantities that are entirely outside our experience. They are not at our scale. They are much too large or much too small. The smallness of an electron is quite beyond our imagination to conceive, yet we can find out, within limits, how an electron behaves. After we have found that out, we can control an electron beam so that it traces on a TV tube the changing pattern which you are watching at this moment. It is hard to accept that we can control something we cannot imagine. Yet such is the case in electronics. Science is an experience that mankind has never had until our time. That is why it is so upsetting. It is also very powerful.
This is National Educational Television.